Before I call upon the next speaker, I would like to inform the presenters that at the end of this session, they will need to remain behind so that we will get a group photo. Without further ado, I would like to call upon Dr. Quinn Reynolds, who's going to give us a talk on HPC in all the right places, accelerating modeling workflows in metallurgical engineering applications. Over to you, sir.
Great, thank you very much. We've had lots of very, very exciting, interesting talks about extremely awesome topics. Now I'm going to bring everybody back down to earth with something a bit more mundane, but hopefully you'll enjoy it. By the way, go and get some of these cool stickers from 1KSA. They're very awesome. Okay, so yeah, my name's Quinn Reynolds. Thank you very much for the introduction. I'll just be talking today a little bit about how we use HPC in the metallurgical engineering space to help us get to design decisions faster and better. So let's get into it. So to kick off, perhaps I can just give you some context for where I work. I'm from Mintech in South Africa. We're a government research institute focused on mineral beneficiation, and we're based on a large campus up in Johannesburg. We've got a big range of laboratory and pilot plant facilities for all branches of mineral processing and metallurgical engineering. And one of those departments is pyrometallurgy, which is where I do my research. It's great. We basically get to play with fire all day. It's quite awesome. So our main focus in terms of research in the last 5 decades or so has been on an electric furnace technology called direct current plasma arc furnaces. And we've developed quite a number of novel smelting processes for those units. We did a lot of work in the early days on ferrochromium, and that really still motivates a lot of the research that, like the stuff that we're going to be talking about today. Okay, so as you probably know, we've got a very big problem in metal production in our modern human societies. We're producing a lot of CO2, and that's contributing to climate change and global warming and all these other problems. If we include steel, the metal production alone is probably accounting for something like about 10% of global emissions at the moment. So this is not something we have an option about fixing. Unfortunately, fossil carbon as a chemical reducing agent is pretty integral to most smelting processes. So switching away from it is a non-trivial problem. We've been doing things that way for 8,000 years. Now we suddenly have to change a technology that's been working well for 8 millennia. People are looking into quite a few different things to do this. I've listed a few of them there, but one of the most promising ones is using alternative reductants like hydrogen to replace some or all of the carbon in your process. So when it comes to that, there are basically 2 options here. The first is you can try and inject hydrogen directly into the furnace. So that's got some nice advantages, although the engineering at scale still needs a lot of working out. If you don't want to inject directly, another option is to add a pre-reduction stage like a fluidized bed or a shaft furnace in front of your smelter and run that with hydrogen instead. That's quite attractive for a lot of reasons, but perhaps the best one is that you can potentially retrofit it to an existing plant quite easily. You don't have to go and reinvest a whole bunch of capital, and you can use what you've already got. So that's the example we're going to be looking at a little bit today. And the big question that usually comes up is stuff like this. When you put that pre-reducer in front of your process, does the furnace behavior change? It doesn't really look like it should if you look at those flow sheets. More or less the same stuff is going in and out in both cases, but let's maybe take a bit of a closer look and see. Okay, so let's just step back a moment and look at the type of furnace that we're talking about here. DC furnaces use electric arcs as their primary heating and stirring elements. Arcs are nothing fancy. They're just incredibly fast, incredibly hot jets of gas that's been split up into a plasma with free electrons and ions, and that makes them extremely electrically conductive. You're passing a big electric current through that arc, and the interactions between the arc and the plasma fluid that it's made up of really creates a lot of very interesting and complex behavior. And it's important to understand some of that behavior if you're planning to design and build and operate pretty much any kind of open arc electric furnace. So that's what we try to do at places like Mintech. Of course, in this case, we're looking at a brand new process here. There isn't much of a reference point in terms of operating industrial plants or data out there. And because it takes a lot of time and money to run a DC furnace pilot plant, it's sometimes a good idea to explore your problem space in advance using various modeling methods. We've done quite a bit of work over the years on computational modeling of arcs. But the one thing that we weren't able to see with a lot of those very fancy, nice models was the influence of the smelting process on the arc. We were looking at very generic arc behavior. So in this work that I'm talking about here, we came up with a new workflow idea to try and incorporate some of those process effects. And this is just what it looks like. It's very simple, really. We start off with a traditional thermochemical process model, which tells us something about the gas phase in the furnace. We then put that through some theoretical calculations to get the thermodynamic and transport properties of the arc plasma. And then you put those into multi-physics models to see how your arc actually works. And so for our process comparison case, we'll just start off at the beginning here with some thermochemistry. And basically what we did, we took a typical South African ferrochrome type ore, and we compared between just smelting that ore directly with carbon in a DC furnace, the way it's done now, or pre-reducing the ore with hydrogen first in a separate unit and then taking that pre-reduced ore and smelting it. We used a tool called FactSage for the thermodynamic calculations, and we should just note that these aren't very computationally intensive at all. You can run quite large sets of calculations on a desktop machine. You don't really need HPC here. And this is the sort of result we get out. Here we're just looking at the elemental composition of the gas phase inside the furnace over the metallurgical process. This is the case for direct smelting of unreduced ore. You can see that the gas is kind of dominated by carbon, hydrogen, and oxygen, but it does have some metallic species in it, even at bulk process temperatures, so that's more on the left side of this graph here. It's interesting to see that magnesium is particularly volatile, but this is on a log scale, so those values are still only about 1% or less of the total. On the other hand, if we go across and have a look at the gas that we get during smelting of the pre-reduced ore, the picture looks a little bit different, especially at typical process temperatures on the left side again. So you can see here we're getting a much cleaner COH gas with less magnesium and other species contaminating it. But again, remember, we're only talking about fractions of a percent here. The actual absolute change is not a whole lot. So do those tiny fractions of contaminants in the gas actually matter and make any difference? Doesn't look like they should, but to find out, we can take those process gas compositions forward into the second step in the workflow, which is calculation of the properties of the plasma that you would get out of those gases. And those properties are calculated using methods from statistical mechanics. It's a pretty well understood mathematical framework from basic physics, and it just describes basically describes the behavior of large collections of small things. And in particular, it describes very fundamentally how bulk macroscale properties emerge out of the quantum mechanical properties of the individual particles that are making up that material. We combine those frameworks with a useful approximation in plasma physics called local thermodynamic equilibrium. And that basically just means that the chemical reaction processes in a plasma are fast enough that we don't need to worry about species transport effects and spatial distributions too much. And that's generally true for arc plasmas, at least away from cold surfaces like electrodes where non-equilibrium effects can be important. So that then lets us calculate the composition of the plasma species at any point in time and space purely as a function of the state variables. And once we have that composition, we can then calculate all our properties in turn using other methods from statistical mechanics. And those calculations are well documented in a lot of literature, but they're complicated and tedious things to do. So we've spent quite a bit of time developing some open source software tools that do all those calculations for you. So when we set up, then we set up our plasma models using a variety of simple molecules, atoms, and ions that are relevant in the ferrochrome smelting cases. And we ran the calculations over a range of typical arc temperatures up to about 25,000 Kelvin. And this is what we get, this big mess. So here we're looking at plasma from the process gas generated by the smelting of an unreduced ferrochrome ore at 1800 degrees C. The initial elemental composition is coming in from our thermochemical calculations that we saw before, and we're seeing what happens as the temperature in the gas or in the plasma goes up and everything starts to dissociate and ionize and fall apart. The plasma compositions are generally quite complex in these metallurgical problems when we look at all the individual species. So those are all those gray curves in the background there. But we've just highlighted a couple of interesting ones to look at, Fe and Cr, because this is a ferrochrome process, and magnesium, because we saw quite a lot of that in the gas compositions. It's important to note that magnesium in particular ionizes very, very easily. So we already start getting Mg plus in the plasma at relatively low temperatures. And if we switch over to looking at the plasma you get during the smelting of hydrogen pre-reduced ore, the same processing temperature, you can see that we're getting much lower concentrations of the Mg species. There's just less Mg in the gas to start with, so no big surprise there. But it just shows that in this case, the magnesium really is just a trace element in the plasma, similar to iron and chromium. And then from those compositions, we get to what we really want to know, which is the plasma properties themselves. So from top left here, it's the density, heat capacity, and viscosity. From the bottom left, it's the thermal conductivity, electrical conductivity, and total radiation or thermal radiation emission coefficient. The red lines are showing the properties that you get for the unreduced ore smelting case, and the blue lines are what you get for smelting hydrogen pre-reduced ore, so the two cases we're comparing. The gray curves are what we get if we only had the major components, carbon, hydrogen, and oxygen. So we take out all the contaminants, we just look at those, just as a reference. So given that the process gases are already sort of 99% plus COH, it's probably not too surprising that the properties mostly follow those pure COH curves very, very closely. But there are two that really don't. And if we look at the electrical conductivity, down here between 3,000 and 10,000 Kelvin, some of the process plasmas are very different and much, much more conductive there. And then also look at the thermal radiation behavior under 15,000 Kelvin. Process plasmas can emit and absorb orders of magnitude more radiation than plain COH. Again, those are on log scales, those graphs. So that was quite interesting. And now it's time to see if those maybe also still quite small differences really have any effect on how the arc works. So plasma arcs are part of a class of problems called magnetohydrodynamics, and all that means is that arc behavior is controlled by three main phenomena, all of which interact with each other in different ways. There's the Navier-Stokes equation for momentum transfer, which governs the fluid velocities, the energy conservation equation, which governs the temperature field, and Maxwell's equations for electromagnetics, which are governing the electric and magnetic fields. And together, they all couple together, they form a single mathematical system. And because everything's very nonlinear and tied together, we have to solve those equations numerically. In our case, we do that with a finite volume formulation built with the open foam computational mechanics framework, but there are lots of different alternative ways to do this. And we again use mainly open source software for this step because we need to add in a lot of non-standard physics. And direct access to the solver machinery just lets us do that quickly, easily, and transparently. It's also very HPC friendly, which is particularly important in this step because now these calculations are starting to get really expensive, and we'll talk about that a little bit later. So to simulate the DC arcs that we'd get in our different processes that we're comparing, we built a model at something that's comparable to industrial scale. We've got a 50 centimeter arc, so about half a meter, running at 50,000 amps on an electrode 75 centimeters in diameter. We only model the central region of the furnace around the arc itself, so that's a domain about 3 meters in size, and we're comparing the results that we get basically with our different sets of plasma properties under conditions that are otherwise all the same. And if we just take a quick look at the model geometry and the computational mesh that we're using here, it looks a bit like this. Basically, we've got a large cylindrical section of the furnace freeboard gas space and the electrodes sticking down into it from the top. So the top and side boundaries are open, so material can move in and out of them. And the bottom is the surface of the molten bath of processed material that the arc is operating on. So the electrode is the cathode connection, and the bath surface is the anode in this particular electric circuit. Okay, so now we can maybe take a look at some of the results. So here we're just showing a reference case again with the arc running in a pure COH mix. The video on the left is just showing the arc shape with the 6,500 Kelvin isotherm and also the current density distribution on the electrode and the bath with blue and red colors. You can just really see the arc is very, very dynamic and transient. It twists around into extreme shapes as the various forces move it around. And I also should probably point out it's moving incredibly quickly. This whole clip happens faster than you can blink your eye. And the static screenshots on the right there are just showing some information about the composition. So we've got mole fractions of the carbon monoxide and free electrons. And basically you can see that the cooler regions outside the arc are pretty much just molecular species like CO. And only in the body of the arc are we actually starting to get some dissociation and ionization. So now we can compare our two metallurgical process cases. Here are the results for the arc running in gas generated by the smelting of unreduced ferrochrome ore. And yes, that actually is an animation on the left there. The arc is just running very, very steadily indeed, with none of that violent motion that we saw in the COH case. On the right side of the slide, you've got the carbon monoxide and electron concentration fields at the top as before, but we're also showing concentration fields for magnesium atoms and ions at the bottom. The magnesium species do contribute quite a lot to the electron density, and that makes the arc overall quite a lot more electrically conductive. And if we move on to the case of the arc running in gas generated by the smelting of pre-reduced ore, you can see that it's also operating in a very, very stable mode. This happens even though the magnesium and other metallic species are at much lower concentrations here. They're an order of magnitude lower than the direct smelting case. It's a bit hard to see, but we're also getting lower electron densities at the outer edges of the arc column, and that suggests that we'll probably have a slightly more electrically resistive process. Of course, we're engineers. We like to look at graphs and numbers and things. You can look at these things a bit more quantitatively by plotting out things like the arc voltages over time. You can see nicely here how the arc in a pure COH atmosphere is really unstable and transient. You've got a lot of very rapid fluctuations in the voltage signals coming in from those big deformations and changes in arc shape. And in contrast, the voltages for the arcs in process gas are pretty much steady and stable. What's particularly interesting also is the big difference in voltage magnitudes. That's the end result of all those differences that added up from the gas composition and the plasma properties. And you can see it's actually got quite a big effect on the arc. Pre-reducing the ore can increase your arc resistance by 20% or more, and it goes up even more if you assume pure COH gas. You can get your furnace design very wrong if you don't actually get this right. So it's quite interesting. So that's a lot of info to digest. Let's just maybe see if we can wrap it up a bit. So developing this integrated modeling workflow for ferroalloy processes was a fun journey, and in testing it out on a subject like ferrochrome really gave us some interesting insights. I mean, I thought so, but I'm an arc nerd, so, take it as it comes. In essence, what we saw was that very small things make very big differences in this world. Trace elements in your furnace gas composition can have a significant effect on the properties of the plasma that you get out of that gas, and that in turn can cause some really big differences in the arc's behavior and its electrical properties. And those things are important. They can really affect how you design and operate your big expensive furnace. But of course, we are here today to talk about HPC and not furnaces, right? So what about the performance of the various bits of this nice workflow that we've put together? So starting off with the computational load, as we mentioned during the presentation, the thermochemical model is really lightweight. It doesn't need a lot of compute. The properties calculations are a little bit heavier, maybe an order of magnitude or two more, and the MHD model is by far the most expensive bit. It's an order of magnitude or so higher still. And that kind of matches up with the kind of resource that you need for each of those steps. For the first bit, you can get away with doing everything on a single machine quite easily. For the second bit, you might need a little bit of HPC or at least a very powerful desktop. For the second bit, you need proper HPC facilities. So this is not a symmetrical thing. You need different resources at different points in the workflow. It's also interesting to look at what kind of workload each of these steps involves. So thermochemistry and statistical mechanics really involve lots of small independent calculations. They don't need to communicate, so the whole thing is embarrassingly parallel, and it scales extremely well. MHD, on the other hand, is a computational mechanics type workload, and that's more classically constrained by trade-offs between compute, communication, and memory speeds. And again, the type of compute load really leads on to what kind of architectures are good accelerators for that workload. In particular here, we're starting to think about things like GPU and many core systems, which are rapidly becoming the norm in large HPC facilities. And what we see is the first two steps in the workflow would work nicely with this kind of architecture, but the MHD models are going to get much less bang for buck. You can accelerate bits and pieces of those big multiphysics models with many core, but it's still quite hard to get the entire compute load running very efficiently on accelerators, particularly if you have a lot of complex multiphysics. And of course, these days, you can't have a conversation about HPC without asking whether AI can do it better, right? I mean, that's mandatory. So this is an interesting one. I think things with highly complex fundamentals and nonlinear discontinuous behavior, like thermochemistry and MHD, are still quite challenging to do with data-driven methods. And there's also, to a degree, just too much dimensionality in the input and output data sets. There's too big a space to search on the input and output. On the other hand, the plasma properties are actually simpler in many ways, and they have nice smooth inputs and outputs and constrained sort of inputs and outputs as well. So AI is definitely something that could have some use for that in the future. So what we're seeing is that the things that work nicely on modern architectures and can potentially be accelerated with data-driven tools are the two on the left here. But unfortunately, they don't really matter much in terms of the overall performance of the workflow for any particular case. The heavy lifting is all happening over here in the MHD solver. And unfortunately, that's one part of the computational load that we can't easily alleviate just by throwing GPUs and AI at it. Of course, just because it's hard doesn't mean it's impossible. There's a lot of people much cleverer than me working on exactly these topics as we speak. So let's see where that all goes. I think it's a bit of natural selection, really. HPC environments worldwide are changing to suit many core compute and AI workloads. And our old MPR-based CPU codes are just going to have to evolve or die off and be replaced by something better. And that's really, I think, the final message from me. As researchers in an applied technology space, we sometimes get very attached to certain ways of doing things. And if you're not careful, that can become a comfort zone that it's surprisingly hard to dig yourself out of. If we're really going to fix the big problems in the world today, we need to be creative. And we'll need to be flexible, and sometimes we're going to need to change our minds, just like Leary said there. So that's it from me. I hope you enjoyed the presentation. Just some acknowledgements to the various organizations that supported us in this study, especially CHPC, of course. They've been incredibly helpful, and without their facilities, we just couldn't do any of this work. So we really appreciate their participation and help. Thank you very much.